Dear colleague, I'm going to present data on HMO and the preterm infant clinical relevance. First, I'd like to disclose that this presentation was funded and an honorarium received from Nestlé. In term-born infants, the total number of bacteria is about the same as the total number of human cells. These bacteria may be divided into beneficial bacteria with a positive effects on functions in the body, neutral type bacteria, or harmful bacteria. The mostly represented beneficial bacteria in term-born infants is bifidobacteria. But what about premature infants? We don't really know what would be the most beneficial bacteria in these infants. We don't know either whether microbiota and morbidity may be related in premature infants. In the EpiPage 2 national cohort study in 2011, we evaluated 3,161 premature infants. Their gestational age ranged between 24 to 41 weeks. In this cohort, 106 infants presented with necrotizing enterocolitis over a stage 2 of Bell. The infants had a higher risk of NEC in case they had a slower rate of feeding or less breastfeeding. In a subset of 94 cases, we were able to evaluate microbiota. Indeed, we showed that microbiome was associated with NEC. As you can see on this graph, we have the NEC cases in black and the controls in gray. The infants most colonized with Clostridium were most likely to present with necrotizing enterocolitis in this study. Interestingly, the infants colonized mostly by bifidobacterium did not present any NEC. In the EpiFloor study, 577 infants from the EpiPage 2 with stool analysis at 1 month of age were followed up to 2 years postnatal age. The gut microbiota was grouped into 6 clusters in the study, 1 cluster being not amplifiable because of too low bacterial load. Then we have 5 other clusters. The first one mostly represented with Enterobacter, the second one mostly represented by Clostridium, the third one by Escherichia coli Shigella, the fourth one by Citrobacter, and finally, the fifth one by Staphylococcus. In this study, we showed that gut microbiota was associated with NICU practices and 2 years clinical outcome. First thing, we demonstrated that cluster 4 and 5 was significantly from infants younger than cluster 3 that came from more mature infants, and that was taken as a reference for that reason. When we compared the different clusters, we observed that for late onset sepsis, skin to skin within the first week of life, or breastfeeding within the first week of life, the more mature cluster was significantly different from the Enterococcus, Staphylococcus, or no bacteria cluster for all of these parameters. When we looked at the 2-year outcome with a criteria of evaluation that was DEF or neurodevelopment assessment with age and stage questionnaire below 185, again, we observed a significant and important difference between the infants who had a more mature cluster at birth, rather at 1 month of age, rather than Enterococcus, Staphylococcus, or no bacteria. Then we would like to modulate microbiota. Besides maturation of the infant, microbiota may be influenced by prebiotics. Among them, HMOs such as 2-fucosidlactose have been demonstrated to beneficially influence microbiota. Human milk oligosaccharides represent up to 25% of human milk carbohydrates. They are indigestible for the stomach and the intestinal tract. They are represented from 5 elementary units such as glucose, galactose, N-acetylglucosamide, fucose, or sialic acid. They are made of a core of lacto-N-bios, where is branch unit of lactose and either a unit of fucose or sialic acid. HMO are not only prebiotics. They have been shown to also have direct antimicrobial property. They may have anti-adhesive possibility. They may be epithelial cell modulators or even immune cell modulators. This slide shows the association between microbiota and HMO. In this study, Corpola et al. Compared the microbiota of infants born by vaginal delivery or by cesarean section. They also compare in these infants those who received HMO in their mother's milk, either when they were born vaginally or by cesarean section. The authors showed that there was no difference whether the infants received or not HMO in their mother's milk when they were born by vaginal delivery. On the contrary, there was a significant difference in favor of the infants who received HMO in their milk when they were born by cesarean section. Overall, the authors concluded that 2-fucosyl-lactose HMO in mother's milk may alleviate the effects of cesarean birth on infant gut microbiota. That study was performed in term-born infants. HMO content in human milk may be very variable. This may be due because of maternal genetics. It has been shown that the mothers may have a secretor profile for specific HMO, such as 2-fucosyl-lactose, or a non-secretor profile. Likewise, that has been shown that there is a significant difference when the mother delivered previously with less 2-fucosyl-lactose in their milk than they were born at term, and that lasted for 3 weeks. In 63 different mothers, Gabrieli and colleagues confirmed that there was some secretor mother and some mothers with non-secretor profile. They showed that for specific HMO, there may be some non-detected HMO in the milk or high level, and they also demonstrated that again for specific HMO, there may be a significant difference between the rates of the HMO in the colostrum or in more mature milk. Of note, that was really seen for specific HMO, but not all of them. Moreau and colleagues showed that there may be an increased risk of necrotizing enterocolitis and late-onset sepsis in 410 neonates with a gestational age of 28 weeks, ranging from 23 to 32. And in this cohort, 1/3 of the infants had mother with a 2-fucosyl-lactose low secretor phenotype. The authors observed 26 dead. 15% were from the low secretor group versus 2% in the high secretor group, and that was statistically significant. 22% of the infants presented with necrotizing enterocolitis versus 7% in the high secretor group. That was significant. And again, gram-negative late-onset sepsis was higher in the low secretor group rather versus the high secretor group. In this study, Maisy and colleagues showed that a low level of specific HMO may be associated with NEC. They performed an HMO profiling in mother's own milk in infants with NEC versus controls. They showed that the level of a single HMO, that was here this DSLNT, was significantly lower in mother's own milk received by infants with NEC. They calculated a threshold level of 241 nanomole per milliliter, as you may see on this slide, with a sensitivity and specificity of 0.9 for NEC. When they performed a microbiome analysis, they showed that there was a lower bifidobacteria and higher Enterobacter cloacae relative abundance associated with DSNNT level. Finally, Morrow and colleague again showed that HMO may be associated with a protection against diarrhea in breastfed infants. In this study of 93 breastfeeding mother-infant pairs, studied from birth up to 2 years postnatal age, they evaluated milk samples obtained from 1 to 5 weeks postpartum. They divided their population into low, intermediate, and high levels, defined by the first, second, or third tercile of the population. They showed that regarding the level of 2-fucosyl-lactone in milk, there was a significant risk of Campylobacter diarrhea when this level was too low as compared when it was intermediate or high. When looking at the whole fucosyl oligosaccharides in milk, again, they observed a significant higher risk of severe diarrhea with low level as compared to intermediate or high level. Well, all these studies raise the question on may HMO supplementation have a benefit on microbiota and beyond in preemies. Clinical safety and efficacy data are required in order to address that question. This is why we performed an intervention study on the effect of a liquid supplement containing 2 HMO in preterm infants. The goal of this study was to demonstrate feeding tolerance among preterm infants measured by non-inferiority in days to reach full enteral feeding in the HMO versus the placebo group. Shorter time to reach full enteral feeding would be an indication of adequate gastrointestinal tolerance and helps to provide sufficient nutrition to assure growth and impact the outcome. Secondary outcome would be growth parameters, gastrointestinal symptoms, adverse events up to 12 months corrected age, fetal microbiota, gut maturation, and breastfeeding HMO composition. Here is the protocol of the study. The design was a prospective, randomized, double-blind controlled trial in 27 to 33 weeks gestation infants in French centers. Early administration after 24-hour feeding was advised, and in any case, before 7 days postnatal age. As you can see here, when the infants had 24 hours of trophic feeding, they started the product and was this period of pre-full enteral feeding. Then, when full enteral feeding was reached, an evaluation was done every week up to discharge. Both enteral feeding volume above 150 ml per kilo per day and parenteral nutrition discontinuation was needed to define full enteral feeding. The product is a colorless and odorless solution of 260 milliosmol per kilo concentration of 0.1 gram per milliliter. It is composed of a mixture of 2-fucosyl-lactose and LLNT ratio, LLNT on a ratio of 10/1 and a dosing of 0.125 given 3 times a day as it reflects breast milk composition. It is given before gavage or feeding when the infant is mature enough for sucking. The results. In black, the results of the HMO group, in blue, the placebo group. There was no difference in this study between the 2 groups for gestational age in weeks, the rate of very low birth weight infants or extremely low birth weight infants. There was no difference either for weight for HZ score, length for HZ score, head circumference for HZ score at birth. There was no difference for the rate of small for gestational age infants. The sex distribution was even. There was no difference for cesarean section. And the postnatal age of the first product administration was identical in the 2 groups. About the exposure to intervention and milk feeding, there was no difference with the 2 groups, again, the HMO group in black and the placebo group in blue. The treatment duration of the pre-full enteral feeding period was not different between the 2 groups. The duration of treatment during the full enteral feeding period was not different between the 2 groups either. There was no difference for donor human milk and mother's own milk between the two groups before or during the full enterial period. Prevalence of formula feeding increased through the full enterial period feeding in the same amount in the two groups. Primary tolerance outcome. The non-inferiority of time to reach full enteral feeding was achieved in this study. In addition, when we looked at the adjusted mean time to reach full enteral feeding, there was 2 days shorter in favor of the HMO group, but this was not significant as the study was not powered for that. Looking at growth and short-term outcome. When we look at the weight for age Z-score evolution, you have in red the HMO group, in blue the placebo group. As you can see here, there was no significant difference throughout the study for the weight for age Z-score. But when looking at the head circumference for age Z-score, which has exactly the same profile as the length for age Z-score, we observed that there was no difference throughout the study, but as discharge with a moderate but significant benefit in favor of the HMO group for head circumference for age Z-score and length for age Z-score. There was no difference between the two groups for morbidity. We observed low average gastric residuals, ranging from 0 to 3 meals per kilo per day. The mean stool frequency was around 3 to 4 stools per day. We observed 3 NEC in the HMO group versus 2 in the control group. No late onset sepsis in the HMO group and 2 in the control group, and that was not significant for either of these indicators. 1 abdominal distension versus 4 were observed with diarrhea in placebo, and 1 versus 2 adverse event caused product discontinuation. None of these parameters was significant between the two groups. So in summary, we may say that the primary endpoint of tolerance, non-inferiority in time to reach full enteral feeding, was achieved in that study. In addition, we had a trend toward a reduced time to achieve full enteral feeding of 2 days, but this was not significant. Weight gain was similar. Head circumference and length was slightly greater and discharge in the HMO group. So we may suggest that HMO supplement may support improved early postnatal growth. Finally, comparable outcome of gastrointestinal symptoms and gastrointestinal adverse events were not different between the two groups, allowing us to conclude that HMO supplementation is safe and well tolerated in that population. So in conclusion, in premature infants, gut microbiota may show different patterns correlated with NICU practices and immaturity, and may be associated with morbidity and clinical outcome. Microbiota appears to be associated with HMOs in preemies, and specific HMOs milk content may be associated with short-term clinical outcomes such as NEC, late onset sepsis, or even death, and long-term outcomes such as diarrhea or neurodevelopment. HMO supplementation, given as soon as possible after birth, is safe and well tolerated. It supports age-appropriate growth in weight and is consistent with length and head circumference improved early postnatal growth. I'd like to thank you for your attention and thank the core investigators of the study I just presented to you. Thank you very much.